So, complex numbers. We'll be able to perform operations with complex numbers. That means pure imaginary, and some that have both a real and an imaginary part to it. We want to add them, subtract them, multiply them, raise them to a power, and divide them. And then down here at the bottom, we have 5 complex number solutions. And they're saying, using the quadratic formula because those are the explicit instructions on the one that we have. But we can certainly get those by completing the square as well. And so, like I said, quadratic formula, we have you memorize it, but you don't really know where it comes from. Better to use completing the square if you have a choice. So now, we have complex numbers. Complex numbers are that new field of numbers that you found out last year that you didn't know about before Algebra 2. You got to Algebra 2 and you knew all about the real numbers, and then about halfway through the year it's like, oh, we can make stuff up. Well, not all stuff. We just have situations where if you're working on a 3-hour math problem and somewhere along the way you have to take the square root of a negative, but you know you can get rid of it in another 3 hours, you'd say, I need a placeholder for the square root of a negative. And I know the real number system is not going to do that. But if I just come up with this imaginary unit and say, okay, the square root of -1 going to stand for this I piece that I have right here. Then, as I go through the rest of the math, if I figure out a place where I could square it, I'm right back in the real number system. And I would have a -1. So imaginary unit is I, and it is the square root of -1. And the definition of a complex number is any number that can be written in the form a plus bi. That's a complex number. Real number part in front, imaginary in the back. Where a and b are real numbers, the real number a is the real part. It has 2 parts, a real part and an imaginary part. And the real number b is the imaginary part, the part with the little I. And together, they are in standard form when we have the real number part out in front and then the imaginary part in the back. The good news is, really the only new learning we had in Algebra 2 about I was that it was there, and that I equals the square root of -1, but all the math you did with it was math you already know, math you already knew how to do. So this says, which of the following are complex numbers? So take a look at that list. When we say complex numbers, does that mean they have to have an I in them? It doesn't. And that's because, notice this has a real part. So every once in a while, if there's no imaginary part to the number, it's still a complex number. And then, every once in a while, all you get is the imaginary part, and that's called a pure imaginary number. But every single one of these is a part of the complex number system. So the real number system that we knew before, now we can just kind of add another big cocoon around the whole thing and say, now if we include those imaginaries, we have all the numbers we've ever learned, with the square root of -1 in there. So all real numbers are also complex numbers. Seems to me you might get some homework. I remember some homework questions last year about true or false questions that would say, all real numbers are complex numbers, true or false. All complex numbers are real numbers, true or false, those type of things. So working back and forth. All imaginary numbers are also complex numbers. So the first one, we saw an A up there to signify, hey, that's the real number part. There isn't an imaginary part because it's 0 times I. But with these, we notice there's a 0 for the real number part, but there's an imaginary part behind it. So 2 complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Everything's the same. That just makes sense. When we talk equals, that's what equals means. Everything is the same. 3 plus 2i is the same as 3 plus 2i. That just makes sense. For example, x plus yi equals 2 plus 5i. So we think, oh man, look at that, we're going to have to do some complicated math there. No. The only way this is equal is if the x is a 2 and the y is a 5. That's it. The real part has to match and the imaginary part has to match. Absolutely have to. So, what does that mean? Well, it still means we're talking about algebra. Real number parts get added to other real number parts. Imaginary parts can only get added to other imaginary parts. So if we have two complex numbers and we're supposed to add them or subtract them, you can only put real parts with real parts and imaginaries with imaginaries. So in A plus BI and C plus DI, we'd say, all right, well, we can do A plus C. Those are both real parts. And then we'll do B plus D and we'll put a little I behind them because those would be like terms. The math that we do with imaginary numbers is very much like the math we do with variables, any other variable, except we have to notice that. So the algebra will be the same, but when we're done and we see something that says I squared, we say, wait a minute, I'm supposed to substitute, oh yeah, -1 in there for that. That's what happens. So we look at A and we say, well, this is no problem. Basically, you could do what we did when we were combining like terms and say, I'm just going to drop parentheses. The parentheses are just to show us, hey, here's one complex number and we're adding another complex number. And then combine like terms. 7 and 4 is 11. -3i plus 5i will be 2i. So we have 11 plus 2i, and it's in standard form, which is the way we want to write our answers to these. But B, same common mistake that we have to watch out for, whether or not it's x's and y's or i's, and that is you have to distribute the negative. So 2 minus I minus 8 minus 3i would be your first step, just so you don't mess up. And then we have 2 minus 8, which is -6, and we have a -I minus 3i, which is a -4i, or minus 4i, right there. That's not tough, you know, just treat it like it's a variable. So we notice adding and subtracting, nothing new there. We have other things we do with imaginary numbers, and this says many of the properties of real numbers also hold for complex numbers. That would include the commutative property of addition and multiplication, which says A plus B equals B plus A. Doesn't make any difference in the order. Associative properties of addition and multiplication. Associative, what numbers associate with. That would be grouping symbols, so we can use those. And then the distributive properties of multiplication over addition and subtraction. Basically, they're talking about FOIL. That's what they're talking about, so we can still use FOIL. So using these properties and the fact that I squared equals -1, complex numbers can be multiplied by treating them as just algebra. Algebraic expressions is what they are. So remember, I is not a variable. So at the end, what we want to do is think, okay, now that I know I've got I squared, I to the third, I to the fourth, how do I write that? So what we want to make sure is that no powers higher than 1 should remain when we're dealing with I. We should know that I squared is -1, and we should be able to work with it that way. So this says multiplying complex numbers, and we have 5 times the quantity, 3 minus 4i. Go ahead and do that one, and I'll call on somebody to tell me what they get. Maybe you're looking done? Which put? Beautiful. Exactly. You just distribute. That's how you do it. Now I look at B. First of all, I can't stand the dot. They did that on purpose because they want us to look there and make sure this isn't addition or subtraction. Believe it or not, when we take this test, every once in a while, somebody will see this on the test, and they will do FOIL. It just happens every year. You know, you go too fast. You want to check between them. What's the symbol? This one is addition. That is not addition. But it is a binomial times a binomial. That's how we treat it. So we're just going to do FOIL on it. So we would say, all right, first times first, 2 times 5, that's 10. Then we have outside times outside, so 2 times -I, that will be a -2i. Inside times inside, we'll have 3i times 5. That's going to be plus 15i. And then last times last, we'll have a negative 3i squared. And that got kind of squashed, so it doesn't look right. And we have FOIL guide. So you know you've done all the distributing that you need to do. When you get a little FOIL guide there. And then we just combine like terms. That's it. So we have this 10, and we're thinking, well, I'm not going to do much with that, but I've got a negative 2i plus 15i, that's going to be 13i, and we get to that last one, and we should be saying to ourselves, wait a minute, I squared is negative 1. So there is more I can do here, because negative 3 times negative 1 is plus 3. So now I can do 10 plus 3 is 13. Plus 13i. So the math is the same, the algebra is the same, when we do FOIL, but when we get done, we have to keep in mind I squared, have to make that a negative 1. So down here, got a little chart to fill in. It says, raising a complex number to a power, raise I to the powers 2 through 8. Okay, so I start thinking, well, I to the first, that's just going to be I. There's nothing I can do with that, but I squared, well, that's really the square root of negative 1 times the square root of negative 1, which, if you do the square root of negative 1 squared, you're going to get right back to negative 1. Now, instead of starting over, I know how powers work. I know that to get the third, what I'm supposed to do is multiply that answer by I. So if I want I to the third, I have to take negative 1, and I have to multiply that by I. It's just going to be negative I. And then to get to the fourth power, I'll have to take my little negative I times I. Not t, for goodness sake. I say, hang on a second. That's going to give me a negative I squared. What I squared is negative 1. So that'll give me 1. Huh. Then we'd have 1 for I to the fifth times I. Oh, that's just going to be I. That was nice and easy. Now we go to the 6. I to the 6 will be our little I from the last one times I again. And that'll give us I squared, which is negative 1. Huh, let's see here. There's I, negative 1, negative I, 1. I, negative 1. Well, if the pattern holds, the next one we should have is negative I. And we do that. So I to the 7th equals our last answer, which was negative 1 times I, which is negative I. And the pattern does just continue again and again and again. So I, negative 1, negative I, 1. I, negative 1, negative I, 1. And what we're supposed to see here is I can still be a part of those powers as we go through this. So we have to always reduce. We never want to leave an I that has a power bigger than 1. So, because of time today, Mrs. P had pre-calculus first hour, and she said we need to skip the challenge question. We're not going to be able to do that. If you want to do that one on your own, that is fabulous. It's a nice one. It's a nice one. But we want to get through all the basics today, at the very least. So there will be a couple of tougher problems in your homework too. So we'll build up a little bit. Complex conjugate. Hopefully you remember this from, hey, if we had an I in the denominator, that's bad news, because I is the square root of negative 1. You can't leave that there. So what we do is we use this process of complex conjugates to get that. So if you have a z, which is a plus bi, then the conjugate of that, notice this was a little bit of new notation for us here. There is a segment symbol above these to indicate the conjugate. That's going to be a minus bi. So what we see here is, really all that changes is the sign between the two terms. That's it. So the only thing that changes is the sign between the real part and the imaginary part. Why would they do that? Why would they change the sign? It's because of what we already know. This is called the sum and difference pattern. And we've done this a ton where we say, okay, it's going to be first times first, and outside times outside, and inside times inside are going to cancel out because they're exactly the same. Then last times last will be negative a squared. And hopefully you look at that and you go, oh, that makes perfect sense. Because if we have an I and we square it, we'll be back in the real number system. That's what we need to do. We don't want any imaginaries in that denominator. So their question is, what is the conjugate of 5? Well, if there's just a 5 out in front of this thing, it's 5. You don't do anything with that. But the conjugate of 5i, well, we're always supposed to take the negative of whatever that imaginary part is, which sometimes seems silly if that's in the denominator, but if you always follow that pattern, things will always go well. So to divide complex numbers, simply multiply the numerator and the denominator by the complex conjugate. Get that imaginary number out of your denominator because it's the square root of -1. So we want these in standard form, and we see here we have 2 over 3 minus I. So what I do is say, all right, my issue here is that I in the denominator. I need to multiply it by its conjugate in order to make this happen, but whatever you do at the bottom, you have to do at the top. We're trying to keep this equivalent. We're not trying to change it. We're going to change the way it looks. We're going to manipulate the way it looks, but we're not going to change its value. So then we go to the numerator here and say, well, we can do that. That's distributing. So 6 plus 2i over, do a little quick FOIL action on the bottom, and we notice all we really need to do is fool the F and the L. If we do the conjugates right, we don't need the outside times the outside, the inside times the inside. Last times last will be a -I squared, and big light bulb goes BAM! I know I can do more with that, because I squared is -1. Hey, that's going to be 4. Next.
3 times 3.
Oh, thank you. And carried on with my little 3s there, thinking about that last number. Thank you. All right, so 6 plus 2i over 9 minus -1. We can do that. That's 10. Now the question becomes, can you reduce complex numbers? Can we say, you know, they all have a 2 that can be pulled out? And the answer is yes, we can do that. We can do that. So we can reduce all of this. Basically what we're saying is we can factor this and then cancel a 2 out of the top and the bottom. Just to make it a little easier. And we certainly can do that. You know, that's the thing we can do. But now, is that in standard form? No, I'm supposed to have real number in front, imaginary in back. So now you kind of have to think of y equals mx plus b.
Okay, you said you were going to take the 2 out of the top. You have to take the 2 out of the 2i.
So I'm going to have one of those days, am I? Thank you. Gotta slow down. Fixed. No. All right. Thank you. Standard form. Think y equals mx plus b. Well, we have to do this. What's in front of that I if there's nothing there? 1. Now it's in standard form. Real out front, imaginary in the back. Sorry about that, I'll slow it down.
The 2 you took out?
This was factored out. This would be 6 plus 2i if we distributed that back in. I don't know why I left that on there. All right, so let's try the next one. right, what are we multiplying by, everybody?
2
Plus 3i. A little more work for this one, right? Why don't you go ahead and multiply by FOIL on the top. See what you get. Ashley, you already do the FOIL on the top? What you get for your FOIL? Good, everybody? Ashley said she got 10 plus 15i plus 2i plus 3i squared. Okay? Go ahead and multiply the denominator if you didn't already. Matt, you're looking done? Did you get down here?
4 minus 9 squared.
Excellent. Then it's a matter of what do you want to do first. I mean, normally I will go ahead and combine like terms before I switch anything. Actually, I'd like to do it all in one step, but I don't want to lose anybody after my little disaster with the last one. So you combine like terms. And then hopefully light bulb comes on and you say, wait a minute, this is -1. And this is -1. So then you combine like terms again. That's always this last step that's so forgettable. Let's not do this right now. Standard form, exactly. So put her in standard form. Real number part in front. Imaginary back. Okay, let's bring her. You're looking done. Put. Nothing we can do to reduce that one, you know. So sometimes if you don't notice that you can reduce, if you get down to the last step, you will. Let me give you a for instance. On this one, if we had kept this, we would have noticed we could simplify those fractions anyway. Because it would have been 6/10 plus 2/10 I. So it's all about what's comfortable for you, and as long as you do it in the same order every time, you're gonna feel like things are going well. All right, what more do we need to do? Well, they're giving us some complex numbers and saying we've got all kinds of things we can do here. We've got an a plus b, we've got a 2a minus 3b, we've got a 4ab, and we have an a over b. So, go ahead and start work on A, and then I'll call on somebody. Are you done already? Did it seem too easy?
Yeah.
What'd you get?
2 minus I.
Seems too easy, right? -2 plus 4. There it is.
If you write it as -5 plus 2, you're wrong.
You'll lose like a half a point to a point for not having it standard point. Yeah. All right, B looks a little more complicated. Let's see, we have 2 of these minus 3 of these. So go ahead and work through that first step. Take a look up here so I can call on somebody and we can make sure everybody's on the right page. Julia, you got it already? What you got? You're past this step already.
Oh. Oh.
What'd you get when you distributed?
-4 minus 8i minus 12 minus 9i.
Okay, so continue on. That gave you?
Rebecca. 16 minus 17i. Rebecca? Marcy?
No.
Oh wait, JK. Nissa.
This is here.
That's the one. No.
So we take a look at that. And again, it's like, well, do we just distribute and combine like terms? Yeah, that's what we do. All right. This looks like it's going to have a little bit more for us to do. 4 times, and yeah, that scrolled way too far up for me there. That was -2 minus 4i. And we have 4 plus 3i. What would you do first? Order of operations tells you to do what first? Well, yeah, we do have parentheses here. Now, even though you're saying that's because it's a complex number, we absolutely would want to do that first. Distributing the 4 causes problems because people are like, do I distribute the 4 through everything? By the way, no, you don't. You can distribute it through one set of parentheses only. So easier to go ahead and do the FOIL here. So go ahead and do the FOIL, see what you get. -8 minus 6i minus 16i minus 12i squared. What did you do next? Did you simplify in there? Okay. Done yet? Now what do we do? Yeah, finally distribute the 4. And there it is. So again, it's not any different than the other math we would do, except that we have to watch out for I squared. Watch out for I squared. Alrighty, this little bugger was our -2 minus 4i. 4 plus 3i. What are you doing? Because I know you're already starting.
Do you multiply top and bottom by 4 minus 3i?
You sure do. Let's see what we get then. How many of you went ahead and separated it into real number part and imaginary part before you did the simplify? Yeah, and you know, it just drives us bonkers when we see this. So most people would say, you know what, I'm going to pull a 5 out of that. And then do a little reducer. Still not done though when we reduced it, right? What's left? All this coming back to you? Remember doing this in Algebra 2? I mean, I think we've spent maybe 6 days on complex numbers in Algebra 2. So, should we know beforehand when we're going to get imaginary numbers? Yeah, we should. And when we're finding complex solutions and we're using the quadratic formula, obviously, b squared minus 4ac, that comes out to be negative. We know we're taking the square root of a negative, and we know we're doing imaginary. So negative b plus or minus the square root of b squared minus 4ac all over 2a. What about if it doesn't come out to be a negative? Could have 2 real, could have 1 real. So if b squared minus 4ac is greater than 0, so it's a positive number, there are 2 distinct real solutions. Graphically, that means it's going to cross the x-axis in 2 distinct spots. 2 distinct spots. b squared minus 4ac equals 0 can happen too. And that's because your graph just hits the x-axis and bounces off. It's called tangent to that. That's one repeated real solution. Bouncing gives you that tangent that counts for 2 solutions. But if b squared minus 4ac comes out less than 0, which is negative, there is a pair of complex conjugate solutions. They have it down here as complex conjugate pair of solutions. So we can know beforehand. Now, with the quadratic equation, I probably would not do just b squared minus 4ac to check it first. You're going to see that when you're doing a quadratic formula. You'll notice, hey, I'm going to take the square root of a negative underneath here. So, solving a quadratic equation, and it doesn't say I have to use the quadratic formula, so I'm not going to. I'm going to complete the square. So I'm going to move that one over. I have a 1 in front of my x squared, so I don't need to worry about that at all. Do you have the little formula already memorized for getting the number for this slot? All right, so our b value is 1. Again, because that's pure division inside those parentheses, we can distribute that too. So 1 squared over 2 squared, 1/4, plus 1/4, plus 1/4. So if we have -1 plus 1/4, that's going to be a -3/4. Again, think of this as -4 over 4. And then over here, we get a little nervous. It's like, what should go here? We don't need to be nervous. We already did. What did we square over there? So what did we square to get it? 1/2. You just go back one step and say, what did I square to get this? All right, this is squared. And now we can take roots. And here's where we absolutely realize, oh yeah, we're going to have imaginary in here. So we want to think of this as the square root of -3 over the square root of 4. So something nice comes out of that. What's the something nice? I'm going to have to figure out what on earth we're going to do with that square root of -3. Well, you have to think of it this way. As the square root of 3 times the square root of so that you can substitute for the square root of -1 and make that an I. We're going towards standard form. Right now it probably wouldn't matter a whole lot, but we're going to go towards standard form. So what's our last step here? Subtract a half. We've got our little plus or minus, because remember, this is going to come in pairs. When we take the square root, we're going to write our plus or minus piece in there. But right about here, when you take the square root, you know, hey, this is going to be an imaginary solution here. And if you get one imaginary solution, you get two, because they always come in pairs. All right. Looking at the clock doesn't even help me. 57. Yeah, I think it would probably take us longer than we have to go through that challenge question, because there's a lot to keep track of there. So instead, 43210 me. How are you feeling about your complex numbers? Are they coming back to you? Okay. So a little practice, and I think everybody will be okay. Oh, and a reminder here, the homework problem numbers in the gray oval are to be done without a calculator. You know, they have their with the calculator and without the ones. So any gray ovals, they're saying don't do it with the calculator. And if right now you're saying, what, we can do these with the calculator? Well, you can't on the test. But yes, I did show my Algebra 2 students how to do imaginary numbers on the calculator last year, so that when you take the MCAs or the ACTs, you'll know, hey, this is a no-brainer. I can just use my calculator for this. But in here, we're going to want to see everything by hand. So 2, 4, 6 through 9, 13 to 23, 25 to 26, 30 to 32, 34 to 36, 42, 44, 47, and 49. And we were talking this morning, it looks like your test is going to fall next Thursday. We'll finish up the second half of the prerequisites here. We'll finish up on Monday with P7. We'll have 2 days of review, and we'll have a test on October. Oh my goodness, when you come back to school, it's going to be October 6th. Right.
Like yesterday, summer vacation started.